How does energy leave an antenna and travel through empty space? There are no wires connecting a radio transmitter to a distant receiver, yet information can travel across cities, continents, and even between Earth and satellites. The answer lies in one of the most remarkable discoveries in physics, the formation of electromagnetic waves. In the previous lessons, we learned that electric charges create electric fields and moving charges create magnetic fields. We also saw that Maxwell's equations reveal a deep relationship between these two fields. However, an important question remains unanswered. If electric and magnetic fields exist around charges and currents, how can energy travel far away from its source? Why doesn't the energy simply remain confined near the transmitter? Understanding wireless communication requires explaining how electromagnetic energy can detach from its source and propagate through space. This challenge puzzled scientists for many years. The solution emerged when Maxwell realized that changing electric and magnetic fields could continuously generate one another. This interaction creates a self-sustaining structure known as an electromagnetic wave. An electromagnetic wave is a propagating disturbance consisting of coupled electric and magnetic fields. As the wave travels, the electric field and magnetic field continuously regenerate each other according to Maxwell's equations. The electric field and magnetic field are perpendicular to one another. Both fields are also perpendicular to the direction of wave propagation. This unique arrangement allows energy to move through space without requiring a physical medium. Unlike mechanical waves, such as sound, electromagnetic waves can travel through a vacuum. This is why sunlight can reach Earth through space and why radio signals can travel between satellites and ground stations. Electromagnetic waves are capable of carrying both energy and information over vast distances. Intuitively, imagine two people continuously pushing each other on interconnected swings. The motion of one swing drives the other, and the motion continues without either swing remaining stationary. Similarly, changing electric fields create magnetic fields, while changing magnetic fields create electric fields. Physically, consider an antenna connected to an alternating current source. As current changes direction, the surrounding electric and magnetic fields also change. Near the antenna, these fields are strongly linked to the current flow. Farther away, however, the coupled fields become self-sustaining and travel outward as an electromagnetic wave. Mathematically, Maxwell's equations show that changing electric and magnetic fields satisfy a wave equation. The solution to this equation predicts a traveling wave moving at the speed of light. This mathematical prediction was later confirmed experimentally and became one of the greatest successes of modern physics. EM wave formation is the fundamental process behind every wireless communication system. Whenever a transmitter sends information, an antenna converts electrical signals into electromagnetic waves that radiate through space. Radio broadcasting, Wi-Fi, Bluetooth, LTE, 5G, satellite communications, GPS, and radar systems all rely on electromagnetic wave generation. Without EM wave formation, antennas would simply store energy locally instead of transmitting it to distant receivers. At the engineering level, understanding wave formation helps engineers design antennas, optimize radiation efficiency, predict propagation behavior, and analyze communication links. It is one of the most important concepts in RF engineering and antenna theory. EM wave formation represents the bridge between electrical circuits and wireless communication. Inside electronic devices, signals exist primarily as voltages and currents. Outside the antenna, those same signals become electromagnetic waves capable of traveling through free space. A common misconception is that radio waves and light are different phenomena. In reality, both are electromagnetic waves. The only major difference is frequency. Radio waves occupy lower frequencies, while visible light occupies much higher frequencies within the electromagnetic spectrum. Now that we understand how electromagnetic waves are created, the next step is to study how they travel. In the next lesson, we will explore wave propagation and discover how electromagnetic waves move through different environments and communication channels. In this lesson, we learned how changing electric fields and magnetic fields continuously generate one another to form self-sustaining electromagnetic waves. We also saw how antennas convert electrical signals into electromagnetic waves that carry energy and information through space. In the next lesson, we will explore wave propagation and discover how electromagnetic waves travel through free space, materials, and real-world communication environments. If you found this useful, like the video, subscribe, and follow for the next lesson.